Welcome in this presentation. We will present you the result obtained through a formal verification of the QUIC protocol. But before starting, let me present the team. My name is Christophe Crochet and I am a new searcher at UC Louvain. This work has been done in collaboration with Tom Rousseau, Maxime Pirot, Jean-François Sambon, Professor Axel Leguet. It all started from the master thesis Jean-François Sambon and I realized during the last academic year. A first approach to this type of verification has been made by Leonard Dizek and Kenneth Macmillan for the 2019 version of QUIC, using a software called Ivy. They present their work in a paper named Format Specification and Testing of QUIC at the SIGCOMM. Between 2019 and 2021, QUIC has evolved enormously, and a first final version has been released. In our master's thesis, we have taken this approach and adapted it to the draft 29 of the protocol. This is not too problematic as the version is relatively similar to the final RFC. We also improve the tool and apply our verification model on 8 open source implementation, while only 3 were considered in the original work. We obtained substantial results in all of them. The result highlights some ambiguities in the RFC of QUIC. We will start by briefly defining what is QUIC and how we consider it. Then we will explain the formal verification method applied in this work and detail our contribution. Finally, we will present the result obtained on 8 open source implementation. QUIC is a secure transport protocol specified in the new RFC 9000. It is built above UDP and is composed of different parts. On the top, we found the application module, typically HTTP3. Then we have the security module, mainly used for the cryptographic handshake with the use of TLS 1.3. Then we have the QUIC frame data structure used in specific situations. For example, we have the stream frame, which is used for sending data. Then we have the ACK frame, which is used to acknowledge packets. QUIC packets are a complete processable unit that can be encapsulated into a datagram, UDP datagram. Finally, we have the protection module, which is used to encrypt and decrypt packets. RFC or request for comment is a textual document containing sentences describing the expected behavior of a protocol and components over the internet. However, RFC usually lack of formal definitions, which can lead to ambiguities of understanding of the specification. RFC 9000 contains more than 250 sentences containing a must statement that all QUIC implementation must meet. In order to verify if an implementation behaves as expected, the standard method is to proceed to interoperability test, which consists of having several peers from different implementation communicate and see if it works. The main problem with this approach is that it does not allow to highlight the requirements of the RFC that are not met by the implementation by producing an interesting test suite. A solution to this problem is provided by Kenneth Macmillan and Leonard Dizek in a series of work that allow to formally specify a protocol through a formal verification tool called Ivy. So Ivy is designed for infinite state system and is mainly developed by Kenneth Macmillan and Odeon Patton. In order to be efficient, this software uses the Z3 solver developed by Microsoft, which is one of the fastest FSMT solver in the market. It also defines a modeling language for defining relationship, objects, and actions. Then we can model an entire system to be verified automatically by adding requirements, assumption, and assertion on these defined entities. A relation is a predicate with or without parameters that return true or false, whereas a function can return any defined type. In the example, the relation path challenge pending indicates whether or not a path challenge frame with data D and a corresponding connection ID C has been received or not. And the function last packet number return the last packet number associated to an IP address and a connection ID. An object is used to represent a state. In this example, we have the state of a packet, and then we can use action to manipulate the state, relation, and function. In the example shown, we have a requirement indicating that the last packet number must be strictly increasing. In addition to IV, they also developed a methodology called network-centric compositional testing, which is used to formally specify an internet protocol. Let's see how this methodology applied for the QUIC specification. First of all, we divide the specification into different components, linked each other by the input and the output. Such model represent an abstraction of the specification. Thus, verifying this set of components is equivalent to verify the whole system. We can see on the figure below the frame and the packet component. We can see that the input of the packet component are the frame produced by the frame component. Each of these components will typically define an action to group and model all the specification requirements related to that component. This set of requirements is manually extracted from the specification and then formally modeled through IV. In the example below, this requirement is used each time a path response frame is received to verify that we must previously have sent a path challenge frame with the same data. It will be also used each time we generate a path response frame by ensuring that this frame will contain the same data in the previously received path response frame. A solver will also be used to verify that all packets and frames we received meet our formal specification, and will also be used during the random generation process of the packet and frames such that they are conform to our formal specification. The last part that needs to be explained is a component called the shime. This component interfaces IV with the network, allowing to send and receive packets. Note that in this methodology, the tested implementation is a black box. This implies that we cannot have access to its internal state during the testing. All we can see is what is happening on the wire. The application of this methodology for testing is quite simple. So first of all, we start by defining the different parts, different parameters of the test. In the example here, we can see that we define the IP and port addresses used by both endpoints. But we can also define all frames that will be generated by the test and their relative distribution within the packets. This is the main way to control a test. In this example, we can see that we allow the generation of ACK stream, crypto frame, and path response frame. We can see that the path response frame has a relative rate of 5, which will increase the probability of it being generated and selected in the packet in order to manage migration. Note that IV use a Monte Carlo sampling method for this distribution. Finally, we also define the transport parameter that will be used, but this is not shown here. The second point to influence a test is that we can add requirements only on the generated entities. This can have several uses. The first one would be to further parameterize the test with specific version of the QUIC. For example, we can also restrict the generated field value to make the test less random and more efficient. Another use is to generate entities that are not respecting the QUIC specification as defined in the RFCs. This last use was left by the original author as future work, and this is one of our contributions. Finally, we can also define requirements that will only be checked at the end of the test. This allows, for example, to verify that the data have been sent or received during the test, and also allow, for example, to check if the correct error code, if necessary, has been sent or received. Now that the methodology is clearer, let's see what contribution we have made to this formal specification. So, first of all, there were 3 original limitations when we start the project. The first one was that IV only supports data type up to 8 bytes, which can be problematic for QUIC since some fields used by QUIC packets and frames exceed these limits. A concrete example is the connection ID, which can be up to 20 bytes. We managed to partially fix this problem, at least up to 16 bytes, which allow us to test many more values. use. The second point is that some heuristics have been generalized to allow testing many more implementations. For example, initially the model only considered connection ID of exactly 8 bytes, which we changed in order to have more adaptive model for the tested implementation. Finally, we had difficulty to launch and install the project initially. That's why we Dockerized all the software in a container. All these problems are now fixed. So now if we look at the requirements of the RFC, we can see in dark blue that a large part of this requirement cannot be formally verified. This is due to several reasons, such as requirement needing to have information about the internal state of an implementation or when we reason about time, for example. Then in light blue, we can find all the requirements defined by a must statement that Macmillan and Zuck implement directly. Our contribution is represented in green. Note that this part is very much about handling error code by implementation. There is also a category of partially model requirement in orange. This is often the case when the requirement has an impossible part, but is still partially formally verifiable. Finally, in red, there is a whole category that we haven't yet the time to model. This mainly concerns unmodeled packets such as the retry or version negotiation packet. If we look at the test suite itself, we can see that we have extended the test suite from 4 to 23 tests for the server and from 1 to 14 for the client. This new test allows the generation of new frame type, but also the generation of frame and transport parameters that are not defined in the RFC. There is also a whole category of tests that allow to generate invalid frame and packets according to the original specification. Finally, we also perform our test on 8 open source implementations, which are defined in the QUIC working group wiki page. These implementations are quite diverse in terms of line of code and level of abstraction in the programming language. Some implementations are intended for the production use, such as Facebook Move Fast or Cloudflare Quiche, while others are intended for research purposes, as EPIQ from Christian Wittema. Testing all these implementation has produced many results, but before starting going through these results, let's quickly go over the operating mode used to carry out these experiments. First of all, it is important to know that a test is considered as failed by an implementation when during the execution of the test, at least one requirement is not respected, and conversely, it is considered to have passed the test. For each of these tests and implementation, we launch 100 run because, as reminder, we have a random process involved in the generation of these entities, and this allows us therefore to capture more diverse results. We run all of our tests in localhost, which allow us to assume the perfect link of the medium. Let's continue by looking at the overall results that may interest us. As one may expect, violation of the draft by implementation has been observed. This happens when a requirement defined by a must word is not met. A simple example is when a server accepts to receive a frame not allowed to be sent by its peers, according to the RFC. For example, with the new token frame. We face this problem with QUIC, for example. The second kind of problem are crashes and internal errors. We had such problem mainly with count. However, we have seen that these problems were fixed in the master branches of the Git repository. Finally, we identified ambiguities in the RFC, since the format specification of the protocol allows us for an ambiguous requirement to have multiple valid formal model. So this requirement will be explained in the next slide. We can also have a view of a result directly. It's a table presented here. The implementation is a server, and each cell contains a number of successful tests out of the 100 runs performed. Note that multiple migration of the client were allowed during this test. We cannot make interpretation based on statistical model because the result could be biased by the distribution of the error. However, we can still make some interesting observation. We can see that some implementation respects the specification relatively completely. This is the case, for example, for Queen and QUIC. We can see that QUIC respects the specification well, except for the handling of the error, where we think it chooses a custom strategy. The opposite is also possible, as for Kant or EPIQ, which are two more minimalist implementation which respect less the specification overall. We can also take a more test-centric view and see that some part of the RFC are well implemented by all the implementation, such as the requirement for the token field in the initial packet, indicating that it must be of length 0 when a server sends this packet. And again, this opposite is also possible. For example, with the error code requirement, where we see that most of the implementation do not have had code to handle this requirement. Here is the same table, but where the tested implementation is the client. Note that no migration were performed as it is triggered by the client. Testing such feature requires to change manually some of these implementation, which we decide to not do in this work. We can now move on the first concrete example. We found one problem involving connection migration in the move fast implementation. It considers the connection migration as invalid when we just start after the migration after sending the handshake done frame. Note that the disable active migration transport parameter is not set. According to the RFC, the migration for the client is allowed only when the handshake has been reported complete. This happens when the server sends the handshake done frame and is represented in red dotted line. In this situation, we acknowledge the frame and perform in the same time the migration, which is allowed since the handshake done frame has been received. However, move fast sends us back a connection close frame indicating with a message error that the migration is invalid. This is a clear violation of the requirement in the draft. Let's move on the second concrete example, which concerns an ambiguity. We see in the requirement that an endpoint must only change the address during a migration that it sends packets in response to the highest numbered non-probing packet. In the RFC, it is stated that a probing packet is a packet containing only path challenge, path response, new connection ID, and padding frames. A packet containing any other types of frame is considered as a non-probing packet. So the question arises, if we must send this packet to the highest numbered non-probing packet among all possible encryption levels, if so, then in the figure shown, it is the first initial packet with packet number 7, or if we must send or if we must consider the highest numbered non-probing packet among the application encryption level. In such case, then we would have to consider the first 1RTT packet shown in red. Both interpretations of the requirement are valid from a formal point of view. However, the implementer seems to have chosen the application encryption level solution, even if the most appropriate interpretation may seem trivial for an implementer, the ambiguity should be removed. The last example of problem found is an example with EPIQ where we choose to correct and find the error. The error was that when we perform multiple migration in a correct manner, it returns a connection error connection close frame, indicating that the data are not matching. After some research, we discovered that EPIQ was probably using an old requirement from draft 20. We fixed that in a pull request. In conclusion, what is important to remind is that we update the model to draft 29, we increase the test set and perform our experimentation on 8 well-known implementations for the client and the server, and this leads us to find different errors, allow us to highlight some ambiguities in the specification. In the future, we plan to update the formal specification that we have to the final RFC and apply the same methodology to QUIC extension. Thank you for your attention.
All right, excellent.
Thank you for your attention.
Yes. Does anyone have any questions? Okay. We have one from Lucas in the chat, and he says, how many of the test failures were reported to the respective projects? Can you hear? You're muted, Christoph, I think.
We found we found 39 errors, different errors in total for all the implementation. However, we did not list specifically the error per implementation in the paper. But they are in our master thesis where we explain all the different errors we found and so on.
But did you report them to the projects?
Oh,
did you open
no.
issues or no?
No, not because one of the problem is that, okay, we know that one requirement is not respected by an implementation. However, the implementation are usually very big. And since it was a master thesis project, we did not have the time to dive into the code of every implementation to point out where the error was.
Sure. I think it would be useful for some implementations if you could link the master thesis in Slack or here in the chat, so they can look it up. Especially Lucas, who was from the Cloud Side Quiche, which didn't seem to come out of the test very well. Second question is from Nick. Nick is always sad if people skip Microsoft QUIC in their evaluations. So he asks, how easy would it be to also test Microsoft QUIC?
It would be very easy. Usually, you just have to add the implementation, and it's kind of automatic. So you just have to parameterize, with the good parameters, and it can be run like that. It's not very it's a one line addition.
Timo asks, is Ivy still an active project? Or are you or the rest of the group planning to continue working on Ivy?
Ivy has been closed. The project Ivy has been closed on Microsoft on GitHub recently. However, Kenneth Macmillan has made a fork of the project, and yes, now we are currently working on the project, and we will continue this work to find further results.
Excellent. I think you can have some very good synergy with Timo on that as well. I think I've had everyone there then, right? I had a question of myself, which for me always comes up with this kind of thing. How do you know that your Ivy implementation is correct? I put it differently in a typical quote. Who verifies the verifier?
It's an assumption, we do not really verify in somehow that the implementation that the model is correct, but by assumption it is correct, and I don't know really how to explain, but from a formal point of view, the model is the specification. So I don't know really how to explain, but the model is good, must be good from a formal point of view,
But the model is manually extracted from the specification, right?
Yeah, but if a requirement can be formally defined and is not ambiguous, you only have one possible way to formally specify it, And if the requirement is ambiguous, then we have a multiple possible way to formalize this. which can lead to different behavior. But this is a problem in the specification itself. It highlights, in some way, it highlights the problem in the specification. So this is why during the model development, we can identify whether the specification is ambiguous in this part or not. Yeah.
Which is also very useful thing to know in itself, of course. Does anyone else have any more questions? Otherwise, we will slowly be moving on to the next presentation. As I said, I really love this type of work. I think this will be even more useful down the line if people start having new implementations. This might be a little bit late for the more established ones that you tested, even though your results clearly show that there are still issues there. That's what I was trying to say in the introduction as well. It's not because these have existed for years that they're full and complete, and new implementations will be even worse. So I really like that you said that you're still continuing with this project and with Ivy.
And we will try to go ahead the problems and in the next step of the project, we will try to consider the implementation not as a black box, but we will try to link the formal model to the implementation itself in order to point out directly where the error might be in the implementation. So this will be one of our future work.